Alright, I'm doing 2010, number 3. Before I start doing this, though, I wanted to actually talk a little bit about derivatives and integrals for the sine for trig functions. So most of you seniors know this, but when you take a derivative of, I'm just going to write dx, for an equation like this, sine of x, you're going to end up getting another trig function. You're going to get the other trig function. So whether you take a derivative or an integral, you'll always end up coming up with another trig like this, cosine of x. Though in this particular case, I believe the derivative of sine x should just be a regular cosine x. Yeah. But the one thing to realize is what happens if you have something in front of this? Like, let's say this was sine ax. So if you're doing instead the derivative of sine ax, then not only do you get cosine of ax, but you end up having to multiply the front by whatever the derivative of the inside is. That's what's called the chain rule, basically, that you do the derivative of the outside and then times it by the derivative of what's inside. So in this case, the derivative of ax is just a. Likewise, if I want to do d dx sine of x squared, it will look something like 2x cosine x squared. So it's just take the derivative of the sine part and then take the derivative of the inside part and multiply the two. Now this kind of works the other way too. When you take the integral of sine x dx, you end up getting a negative cosine of x. Again, that's on the reference table, so you don't really have to worry about that too much. But what you do have to worry about is when there's something in front. So here, if you have sine of ax dx and you're taking the integral, well, just like with this derivative, how you multiplied the coefficient, you multiplied the whole thing by it, here you're going to actually divide it by the derivative. All right. But yeah, that's what you end up doing. So with the integral, you end up having to divide by the d dx of inside. While here, for the derivative, you multiply by the derivative of inside. Like I said, this is something to help out for the first part. Alright, part A says determine what the velocity of the skier is while it's accelerating. And we're supposed to assume that it starts at rest. So, we know what the acceleration is. So what we're going to say is that the velocity is the integral of the acceleration with respect to time. Here, the acceleration is represented by a max sine of pi t over t. And we're going to do it from 0 to t. So the velocity is going to go, well, a max is a constant, so I can rewrite it like this. Now, forgot my dt. Now, this is going to be with respect to this t. So what I'm going to do is it's going to be a max. The integral of a sine function is a negative cosine function. going to have the same inside, but I have to make sure I divide it by the derivative of pi t t. So the derivative of that is just pi t. So I have to divide it by basically what's inside without the t. And that's going to go from 0 to t. Alright, so all in all, I end up getting negative am for a max t over pi cosine of pi t over t from 0 to t. So I'm going to end up getting negative a t pi cosine pi t over t minus negative am t pi cosine of 0, which is just 1. This negative makes that. So I end up getting am t pi minus am t pi cosine of stuff. So let me just rewrite this. Basically, I end up coming down with the equation to be am t over pi 1 minus cosine of pi t over t. And that's what I end up getting. And you end up getting a whole bunch of points. Like you got a point for basically stating that the velocity is the integral of a dt. You got a point for using a sine pi t over t in for that. You got a point for doing the integral properly. And then another point for basically continuing the continuing the integral. So you got 2 points for the integral actually. I'll just change that to 2. So that was where you got your 4 points. Alright, for part B, it wants to know what is the work done by the net force on the skier from rest until terminal speed is reached. Alright, so there's a few ways to go about doing this. The easiest way that I would say is to just look at energy. Basically, the work being done is just by the net force is basically being done to put in for kinetic energy. So this is going to be equal to 1/2 mv squared minus 1/2 mv0 squared, but starts at rest, so that's just 0. We know what the terminal speed is, so if you remember our equation for the velocity was a t pi 1 minus cosine of pi t over t, but it stops accelerating when little t is equal to big T. So I end up being left with cosine of pi. So that means it's going to end up moving at a constant speed of 2 amx t over pi. Alright, so the work is equal to 1/2 m. This is my v squared. And I end up coming up with 2m a squared t squared over pi squared. This was 2 points. 1 point for determining the final velocity, and 1 point for realizing that work is equal to change in kinetic energy. Okay, part C. It's saying that they want to know what the work is. Not the work. The force exerted on the rope by the skier at terminal speed. Now this is easy because if you remember, when we're talking about terminal speed, that means the net force equals to 0. So the force that's pulling him up must be balanced out with the force that's pulling him down. So if you remember, we have mg sine theta pulling down, and the applied force from the rope going up. So because F then equals 0, that must mean that these two must be equal. And these are all constants, so there you go. That's all you have to do, and of course it's only worth 1 point for something so straightforward as that. Alright, part D, they want to know what is the impulse during the acceleration. So because of the fact we're talking about during the acceleration, that means we're going to have to do some sort of calculus, because the acceleration is constantly changing. And remember, impulse is force times time, so the calculus version would be the integral of force with respect to time. And that's going to be equal to ma dt, m integral of a dt. Now the interesting thing is that we kind of already know what the integral of a dt is, though it's going to be from 0 to big T. So during the entire time during the acceleration. Now we actually know what a dt is. We got it before. It was a m t over pi. What was it? Cosine. Oh wait, 1 plus cosine. Sorry. One plus of pi t over t. Actually, you know what? Let me rewrite this. So the integral of that ended up being cosine of pi t over t. And we're going to do it through the bounds of 0 to big T, which is m a m t pi. It's supposed to be negative. Cosine of pi minus cosine of 0. And you should end up getting 2m a max t over pi as your impulse. Another way that you could have done it is you could have just said that change in that impulse is just change in momentum, which is m change in velocity, and it goes from mvt to from rest to vt, so it ends up being this. And then from before, the terminal speed was 2at over pi. All right, and this was 2 points, really based off of whatever you did. But one of the points was getting the answer, pretty much so. Yeah, this was 2 points for everything. Last part, E, it says, alright, they say that the acceleration is represented by the equation a max e to the negative pi t over 2 big T. And they want us to show what the equation, what it's going to look like for the 2 scenarios. So, and it's the force. We're going to do force as a function of time. So, let's see. Alright. They actually have this written out. So the thing is, this acceleration is going to end up basically decreasing until it gets to that value. So it's actually going to, if you think about we're doing the net force, right? No, the force of the rope. So in the original scenario, it was if we did F net equals ma, it was equal to mg, that should be sine theta, mg sine theta plus m times a sine of blah blah stuff. And in the second scenario, it's mg sine of theta plus ma e to the negative pi t over 2t. So basically what you have to realize is in this scenario, as we change sine from 0 to big T, this equation ends up going from sine of 0 sine of 0 to sine of pi. So it ends up going from 0 to 1 to 0. You know, as it goes up from, I should say, sine of 0 to sine of pi over 2 to sine of pi. So during the whole range that it's accelerating in, the value of the ma sine theta ends up going from 0 to 1 back to 0. So that means that in our graph, in this range, the graph for the original force should start off at this mg sine of theta, because again, at t equals 0, sine is 0, so this whole thing goes to 0. And then it should go up to some maximum value, and then it should come back down to 0. And this maximum value ends up being mg sine of theta plus ma max. Alright, now this was for scenario 1. Now for scenario 2, again we're going from t equals 0 to t equals big T. When little t equals 0, then that means we have e to the 0, which I want to say is equal to 1. Let me just double check. E to the 1. Oh, wait, sorry, e to 0. Yeah. So e to the 0, which equals 1, which means that F2 equals mg sine theta plus ma. And then when it equals tau, when little t equals big T, this ends up being e to the negative pi over 2, which is equal to negative pi divided by 2. Yeah, which ends up equaling some fraction, so like 0.0207. So what we end up getting is that in the second scenario, it's going to start at that same max that the first force ended up reaching at some point, but instead of it going up, it's actually just going to go down. And it's going to go down like this. Because as t gets bigger, the value of that e, of this e, ends up getting smaller and smaller. So it basically adds less and less to the force, to the mg sine theta. And that's why it ends up going down. This one was definitely probably the trickiest one, and because of that reasoning, it was worth 6 points. So you ended up getting, most of the points actually came from the first graph, realizing that it starts at mg sine theta, realizing that it basically ends up looking like half a sine curve, for realizing that it returns to mg sine theta at t, and actually I forgot to mention that after it reaches this, it just levels out. So you got a point for realizing that it becomes a constant speed after the fact. Alright, so the 4 points were all for F1, for the original scenario. For F2, you had to realize that for 1 point, so this was for F2, 1 point for knowing where it starts, and 1 point for realizing that it was a decay curve. Like I said, this was definitely the trickier one, and really what you wanted to see was how did this term in both of the scenarios change as time went on. For the sine curve, it's going to go on like this. It's going to start at 0, increase some amount, and then decrease back to 0. Well, here it's going to start at 1 and then slowly go down to 0. So the effects of this goes straight down to 0, while this one oscillates back and forth from 0 to 1, and if we continue going on, would have went down to -1. Alright, so if you have any questions, let me know. Keep practicing these problems, and let me know the moment you have a problem.